he just kept going, and so he had a lot of ground. So it was great.
Okay, I think we're live.
Gotta be good.
It's good. It's a good key up for the book, you know.
You guys out there hear me?
It's like a synopsis of what's in the book.
I want to get.
I just get some live.
There we go. Okay, Marcus, I can see your screen.
What are you gonna do in San Diego?
Well, my son has a surf camp.
Surf camp?
Matt, did you say you can see my screen?
I can see your camera. Sorry,
Good. Okay.
Just middle of the
trying to get settled here.
Yeah, so I mean, you wouldn't have to go to San Diego just because your son's at surf camp. But you're good.
You guys out there
Yeah.
watching, seeing this, or hear
You
me?
just come down and visit everybody.
Can hear everything?
You're gonna be where your kids are.
Try and set up our.
Yeah, okay, well, it used to be you
This
would
is what I
take your
usually
kids,
do,
and
like
then,
this here.
now it's like
I can
wherever
hear
they
great.
are, you're gonna see if they let you come along with them. Here we go.
Try to give you two
Wow.
views
Yeah.
if I can.
Well, somewhere else. Well, when your kids are my age, that's what they'll be like. You don't tell you when they're going on vacation. It's like, oh yeah, tomorrow we're going to Germany. Oh yeah.
They're just chatting with their kids about their kids.
Well, while I was camping,
So here, we're doing something fun. It's like, we always take our boat up to the dock in the summer, right?
I need to
And
turn.
when the kids were little, they
Turn
always
this
went
off.
to school kids.
Yeah.
Okay, I'm gonna turn this off.
You know, Anne has been up with us now for like 12 years because she's 29. And but she and her husband are going to go with us. So it'll be very interesting. We're going to be very close quarters for 4 days.
Nice.
It's like, my gosh, you can't even step on land, right?
Oh,
4
wow.
days, right? You're on the boat, you can swim, kayak. You know, but we'll see how it works out. They seem excited about it.
Okay, I think we're ready to get started. I'll start our recording. Okay. Yeah, so what I'm presenting today, there's no huge revelation. It can be summarized in a sentence that we make different assumptions about what neurons can do and capsules make, and that causes a different theory to arise of what a neural system should do.
So you're saying is this like a comparison between capsules and what we've been
Yeah.
thinking? Is that sort of?
Yeah, it's a comparison. It's showing like design principles for, neural circuits if you want them to handle the world. It's an interesting question of how, like, the fundamental question of what can a neuron do really influences the way that the design direction that those will take, the direction they'll take, and what algorithms they'll tend to use. And so I'm going to talk about our model capsules and how the underlying assumptions are what really drove them to be where they are. And it's just cool to talk about the assumptions themselves. Topic title, representing pose, pose being location and orientation. Like, for example, the pose of this is changing, the pose of it's changing when it rotates. And also I'll throw into this representing, when I get to it, the point is, sometimes I'll also talk about the size of the object, scaling of it is also kind of represented. That's strictly speaking not pose. Sometimes I'll just be sloppy and say pose to describe all of it. This picture is basically using notation from Hinton's 1981 papers. This idea of having some circuit that transforms between reference frames and building an object recognition system on that.
R stands for reference frame. Yeah, I forgot.
Here R is, oh yeah, I should have said
For
that.
that.
Here R is spatial relationship.
Relationship. So it's like relationship of the object to the sensor, the object to the component, component to the sensor.
Yeah, so R is, spatial relationship between these. And so here, like our compositionality model, this is pretty much exactly a drawing of it, where like this is, one way we might interpret this is a location in the space of a child object, and this is the location in the space of a parent object. And this is displacement cells. This is something that represents the transform between those two reference frames.
So quick question, and clarify. When you say our object, comma sensor, is it the location of the sensor in the object's reference frame?
The way
the relative.
the way I'm doing it, this is going to be, now this isn't fundamental. Everything I'm saying, okay, answer to your question, no, it's the opposite. In the notation I've chosen to use, this means in the sensor's reference frame, where is the
Where's the
object?
object? Okay.
That's what I mean by this notation. I could talk why I used that one. However, if I had answered the opposite, everything I say would still be
Yeah,
applicable.
they're kind of duals of one another.
Yeah, yeah, one's the inverse, so like they're one-to-one mappings between them. Very closely. It describes capsules kind of conceptually, but capsules make an additional change where they don't have this neural population that represents the spatial relationship between things out there. The no population represents that. They pull that into. I've taken this letter and I've stuck it inside the triangle. I've stuck it inside the flux capacitor.
Why did you do that?
Oh, just to say that now that it creates one of these, a similar transformation circuit that takes one of these and gives you one of these. But they've removed like this third input to it. This third input that configures what happens.
Oh, so this is capsules then?
Yeah. So capsules, this variable.
So, but he described it in his 81 paper like up above.
Yeah.
He started out with a similar diagram that we have.
Yeah.
And in the capsules, did they change or did they just phrase it differently?
They move that representation from cell activity to cell weights. So it's still a number that now, rather than living in a set of neural populations, now lives in a set of synapse parameters and connections. And the premise, what caused me to walk away and think about this was, why did they land on something a little different from us? Why did we land on this idea that you need some population that's representing that, where they're somewhere else? Because there's so much else, so many other common conclusions we've
Well,
reached.
the first thing that would pop to my head is something we've talked about a lot here, which is the idea that you need to do a very extemporaneous representation of displacement, which can't be done with neuron weights. Is that the short answer?
That is an answer, but I could give you a comeback to that.
I'm not trying to. Okay.
So, but if you want the extemporaneous representation, this quick, like, all right, I see a chair, a robot, and I want to represent that arrangement. Well, you could just continue keeping all of that in your viewer-centric coordinates. You could just, the initial buffer, you're like, okay, there's a chair there, a robot right there. I take a step forward, I update all of those.
Yeah.
You could keep those temporary buffers all in a.
Yeah, but the problem with that is, if I'm going to learn that, ultimately I'm going to learn that. Right?
Yeah.
Then I have to have these two populations of cells. I'd have to keep them active throughout that entire learning process. Okay, I don't want to get off on that tangent here, but
So it sounds like you're saying this doesn't actually handle it, in this framework will handle it some other way, like viewer-centric coordinates or something.
Sure, but
So this doesn't actually handle
there's
it.
not a fundamental need. This system could. The system can handle that situation, is what I'm saying.
Here's another situation, for example. If for example, if I was using displacement cells as my means of pitch independent melody memory, right? That's one of the examples I have. Like I'm trying to remember the structure of things independent of specific implementation. Then I want to learn a sequence of displacement cells. I can't learn a sequence of synapses. I mean, I could represent the displacement here in the synapses once, but there seems to be a huge value in having a representation that's a displacement representation. I mean, it just seems that way to me.
Yeah, and an example I would have used there rather than the song one is, well, you use the stapler or like glasses. Like right now, if this is a spatial arrangement of like these three components, when this moves.
Oh, yeah, right, exactly.
When this moves, it's like what you're doing is updating this population right
Yes,
here.
yeah.
And it seems nice to be able to store sequences of these.
Yeah, that was in the framework statement.
Yeah.
That's the idea, the statement, right?
So
Yeah.
totally, I don't have a comeback to that.
Well, maybe we
That
don't have to
is-
accept this as right, this
Right.
is just what they did, right? This is what Capsules has today.
Yeah, so I do think that what we just brought up, you at the pitch, me at the classes, is probably the big fundamental benefit that there is no comeback for. That is really good
Yeah.
about our system, but like there might be other ways to get that.
Okay, but you're gonna explain why they went this way.
Yeah. So okay, I pretty much said everything here. So yeah, I mean the topic is representing pose in kind of three different ways with numbers, neurons, and capsules. So first, to dive into the numerical way of talking about this, a numerical way. One straightforward or one like common way of representing spatial relationships is with, so this is a 4x4 matrix, and it's an affine transformation matrix where and I'll just break down these components of it. One of these is this 3x3 one. Inside of it is the orientation, which I've described as a rotation matrix, and some scaling. The scaling indicates the size of the object. The S is kind of this part's kind of optional if you don't want the system to be able to have this notion of a giant cylinder after it's learned a small cylinder. You can remove the S. And then the 3D location of, so this is like an XYZ of the sensor in the object's space. If you take those variables, choose to express it as a matrix like this, then it's really simple to operate on. It's really straightforward to operate on. I'm just laying out the problem of what is pose, or what is one straightforward way to represent it. And just so I can get to this fun aside, I'll also say that you can also represent it as the inverse of that, where rather than representing the location of the sensor in the reference frame of the object, you represent the location of the object in the reference frame of the sensor. And this is kind of a fun discussion of which of these is right. Because as we've had.
We've had this kind of a lot. I don't remember it being fun, but.
So, right, like, well, the interesting thing is, I'll just read this, like, this is when the object rotates, does the location move in circles around it? Right now, when you see this marker rotate like this, are you doing somersaults around the object? Or not? The flip side is, as you saccade your eyes, is the location of this marker changing? In one of these systems it is, and one it isn't.
Couldn't you have both? I mean, couldn't this be the what and where thing, right? You could have both this going on?
Yeah, one of these is really good. This one is where's the sensor in the reference frame of the object, is very much inspired by grid cells. It's like your finger is the rat, your eye is the rat. This one, the object is the rat.
Yeah.
And it's like, so as the object rotates, its head direction cells are changing.
It seems in the end, after we brought up this and got confused about it a lot, that it seems like both are necessary. Almost, it seems like that, or it would be very copacetic to have both, and one could be a where path and one could be a what path. And by the way, that doesn't mean we're always doing the first one. Maybe we only do the first one when we are tending to object space, or tending to, thinking about more about how to structure things, right? So it doesn't mean they're both occurring all the time. Might, but doesn't mean that. I'm saying that to see if you agree. I'm interpreting it correctly. Okay.
So one quick statement that can be made about this location of the sensor. This is good for path integrating the sensor. This is good for taking movements of the sensor and path integrating it. This one's good for path integrating the object. If, as you see the object rotate, as you see it shift around, updating this is really simple. Whereas both of them are awkward in the opposite. This one, if you see the object rotating, you're like, oh no, now I got to make big circles around it. Whereas this one, the point is they're both awkward in the other domain, and they're both really nice in their own domain. So that was the aside. Now, so yes, numbers can represent poses using these matrices. It's kind of 4 by 4, but technically you're only using 12 numbers, and the others is just like a hat to make it where matrices can shift stuff around. Now moving into the neuron world, each of these variables, the scaling factor, the rotation matrix, which is an orientation, and the location, well, I'm just going to say things that are familiar to everyone, except, I mean, I'll start with the unfamiliar one. Scalar is some sort of scalar value. It could be something like our scalar encoder. It could be a firing rate, some way of encoding a scalar.
Is that in general, or you were just saying the size of the object?
That's the.
I'm sorry.
This variable represents the actual size of the object.
So couldn't that be the frequency in the thalamic cortical hypothesis? Could that be that? Could the scale be represented by that frequency?
The thing is, I think you want, this is going to become an aside again, but I think you want that frequency to represent how large it is on your retina.
Yeah, I do. So that's not the same?
No, because as you get closer to it, you want that to be, that's like the scale. That's like.
Well, that's what you said, scale. So I was asking, is this a generic scale or is it that scale? You're saying it's not that scale, it's more of a generic scaling issue.
It's something that doesn't change as the object moves.
Okay.
So whereas what you're talking about.
So one would be like the actual coffee cup is bigger or smaller, and the other is how far away is it?
And actually what you're talking about, what you're talking about is actually this.
Okay. It's also, well, one's called scale and one's called scalar. So I was trying to.
Yeah. Oh, sorry.
So it's all right. I was asking the question I was asking. Right, you were referring to that one. The answer is no. When you're talking to S up there, it's not the thing I've been talking about.
No. What you're talking about, I'll get to it in a couple seconds.
That's the answer to my question.
Yeah. So I mean, here is just to state what I'm doing right now. I'm just like analyzing roughly how many neurons do you need to represent this, or what does it even look like for a neuron to represent a matrix like this? I mean, it doesn't represent the matrix, it represents these underlying variables. And these underlying variables, yes, it's a little bit uncertain how a scalar value is represented. That might be a firing rate, it might be some frequency, it might be some population.
Let's go with firing rate.
Okay. Now, I called this rotation because I wanted it to be straightforward how to make it into a matrix, but it's an orientation. And we represent orientations. We know different ways to do it. Here, what I think is the most realistic is probably a point on the surface of a sphere, which is like a reference direction, and a ring. We've talked about that a little bit. It can also be a point in a volume of a sphere. There are different options. Point is, it's going to require a relatively large number of cells. And so there's that. Representing the location with many different options. I just called them option 1 and option 7 just to make it clear that these aren't the only ones. So we have the paper on bioRxiv about how multiple 2D attractors could do it, but each of those have a relatively large number of cells. Another way that is appealing for the thalamic scaling hypothesis, the idea that the thalamus is kind of scaling your input, making the learning problem much easier for the cortex. For that, you want to split up location a little bit differently. This is an aside, this isn't core to my topic, but the point is there are other ways you can say that like the direction from the object to you, and then like its scale, which is proportional to its distance and its size. But the scale, it's just like a scaling factor. Like what would you want to tell the thalamus if you want some scale invariant? If you want the same thing to be arriving at cortex as this is getting closer and further from you.
That's an important distinction of it, because the more and more we've thought about it, or I've thought about it, I'm having trouble with the multiple 2D attractor problem. Everything. It just doesn't seem to fit the biology. So the idea that we could move away from that and incorporate the thalamic idea, which I think is right now, that's an important distinction, I think.
And I do think, you can't do just one of, or rather, if you wanted to move to the thalamic thing, you'd have to move away from this.
Okay, well, that's great. I mean, because as much as I love that, I'm having trouble with it every time I turn around. So, the fact that we just even have a way that does both is great.
Mhm.
I don't think it's ever been expressed that way before, but I think it's a good observation.
So now I've said how to represent it in numbers, how to represent it in neurons. Okay, how do you do it with capsules? Well, the capsules allow their quote unquote neurons to have scalar values. So they can represent size and pose with 12 neurons. This 3x3 matrix, this 3x1, that gives you 12. Whereas our model assumes that it takes many more neurons than that to represent a pose and the size. Anyway, size is not strictly speaking part of pose, but we assume we're built on different underlying assumptions, and it's caused us to go in different directions. And here I'm going to talk about the kind of the design space, the circuit space, the algorithm space that comes from different answers to a couple questions. One of those questions is, can pose be represented and computed succinctly? Is it possible for just have a small number of neurons represent this, or does it require maybe thousands of neurons?
The keyword is succinctly up there.
Yeah.
They both compute it. They
Yeah.
represent it. Okay.
Yeah. The keyword is succinctly. So does it take 12 neurons, or does it take thousands of neurons? I'm just guessing this is thousands, but that seems like a good guess. So there's kind of a spectrum of the right way to, if you the designer are like saying, okay, I have these biological neurons, I'm going to design a really good system with them. Here, and you have this like dial of like, can it be expressed succinctly, or does it require lots of neurons?
One could argue in biology, thousands of neurons is pretty succinct.
It's pretty small.
Fine. But like sometimes Hinton will talk about mini columns as being used, which I'm not totally discounting it. I'm just laying out the space of like what direction you would go based on these premises. So yeah, if pose can be represented and computed succinctly, then capsules seem like a logical direction. Whereas if it requires lots of neurons, it's more like our model. And I would say that like this question, I don't have a firm answer on this. Like maybe neurons do a lot more than we give them credit for. Maybe there's more going on inside of them. Maybe the timing of their spikes actually encodes a lot of information in there. Maybe a surprisingly small number of neurons can actually do a lot. I don't know. And if they can't, then you arrive at something like our model. And then the interesting thing is that like different they really do fork and go in different directions. Each capsule represents, like here, each of these I'm showing, like this is a capsule, this is a capsule, this is a capsule. Each one of them represents like a basic feature, a basic component. Like one of them might be your cylinder capsule, and it has its own set of cells that represent how that cylinder is oriented and scaled and such. Basically, every component, every feature, every object, whatever, has its own dedicated set of pose cells. And you have these, and which of course means you have to have a very fluid notion about what is an object. Maybe an object is actually a population of multiple capsules. The point is that they are these isolated groups, like your cells that represent where's this cylinder, where's this coffee cup, won't even be used to represent where's this this marker.
In some sense, it's sort of like grandmother cells to location. or pose or something like that. Right? You're not sharing them. It's not a distributed representation in a sense that, not even distributed is not the right word. I mean, I can use grid cells to represent many, many maps, right? I can do millions of maps or one big map, or whatever. If I'm understanding what you're saying. But here it's more like, oh no, I can use very few cells to represent a map, but it's just that map.
Yeah.
There's no other map.
Yeah.
Which it's really convenient when you're doing few things, but it gets in the way when you want to do a lot of things.
Yeah. So the way I would think of it is capsules, there'll be a few layers of them. And up top, they have grandmother capsules. There's a cat capsule that I'm just making this up, but like they have individual capsules per object. That's a hack and gross, but everything below is then learning a set of these reusable components that they rearrange in different ways. And yes, there are a fixed number of capsules. It's not like our SDRs where you can just generate them on the fly. So the system's going to learn its features accordingly. It's going to learn like what is a useful, suppose I can learn exactly 1,000 features, one per mini column, suppose. Then like what is the optimal set to learn? You can see it being good for a system that takes components and arranges them. But for object identity up top, it's a hack, it's gross. So I do think there are nice ideas there that are not self-evidently wrong. And then there's a hack up top.
I'll reserve judgment till you get to the other ones.
Okay. So this next one is basically the flip side of what I said before. In this one, a capsule essentially is its pose cells. Or sorry, okay, start that sentence over. A capsule almost is exclusively just a set of cells representing the pose of a particular feature. It doesn't even really represent what feature because those cells are devoted to it. The capsules often will have one other cell that might represent, like, what's the probability that it's there. Conceptually, you can almost think of our cortical column as being a really big capsule that just has a lot more of these cells that identify the component. So it's like we've taken one of these, made it big again.
You're talking about unions there?
No, let me come back. I'm restating the previous point that capsules just are devoted to one particular feature and they orient it. Our circuit is devoted to a larger set of features, a larger set of components, and it arranges them. And then it has to represent which of those is it. Okay. In this design space of algorithms, you have some computational unit. Here it's the capsule, here it's perhaps the cortical column. Inside the capsule, inside for both of them, that computational unit is representing a pose. Here it's very small, here it's very large. The other cells in the capsule here are almost non-existent, where here the other cells in that unit are what is the feature.
Distributed representation, you mean?
Yes.
Okay.
Yeah.
All right.
So I'm trying to, it might be a little bit of a stretch. I'm trying to just like give you this notion of like a smooth design space of how this could all
I don't
work.
see it as smooth. It seems to me almost like on the left side there, we're saying, okay, we can build this computational unit. It's really small, by assuming everybody's got these floating point values. And it's really small, but then I'm limited to, I have to have those things. I'm going to sneeze in a second. Excuse me.
Well, we're prepared.
On the other side, it's like, I don't see a smooth transition between them. It's more like, I'm going to sneeze again. It's like, okay, now we're going to go to this distributed representation. Got some humility in my nose. I guess I don't see it as a continuum. It seems more like a choice, like small and high precision and dedicated grandmothery thing, and then the distributed. It's like grandmothery thing and distributed. Is that too much of a Am I being too binary about that?
I think it is a little smoother than that. The grandmothery thing is,
I could do combinations of these mini columns, something like that. Is that what you're saying? I could do, I assume these are all mini columns. I have 1,000 of these things. I can do combinations of them. Is that the idea? I'm sorry.
okay, so a capsule has some ability to configure like what is out there and where is it. A cortical column can represent what is out there and where is it.
The capsule
So-
does that for using very small number of neurons, but it's dedicated.
Yeah, so the capsule essentially doesn't even represent quote unquote what is out there. It only represents where is it. Because it's already devoted to the what. It's what is kind of fixed. And I guess maybe it's a little bit of a stretch, but I'm just saying like the capsule's only notion of what is out there is just a probability. Where our notion of what is out there is it's like, a distributed representation of some thing.
Yeah.
That's where I'm trying to establish this. I think there is some truth here, but I might be making a little bit of a stretch too. Okay, now to get back to, this one is a little less, I'll just say it, this was the more fundamental one. Second question though, can the transform circuit, can what is going on in this triangle be quickly and easily learned? Suppose you know this, suppose you know this. Can you quickly learn or let's put it down here. Suppose you know this. Can you quickly learn this? Is it just a trivial operation like it is if you assume cells have scalar values and then you just learn of weights that are positive and negative accordingly? Is it trivial to do that? If it is, then it makes sense to do these learn these on demand. You learn these like, okay, this spatial relationship between this component and this component, this child object, this parent object. I'm going to learn it, and I'm just going to learn the entire circuit, whatever is required, and just make that your entire mechanism. Whereas if it's hard, as we've generally assumed it is, if it's elaborate, then you have this you want to have this more general purpose flux capacitor thing that can. What's going on in this triangle is pretty complicated.
Are you assuming it's like the multi-module displacement cells?
Yeah, and that's like the simplest version. That's the displacement cells of displacement routes every grid cell to a different grid cell essentially, and it only gets more complicated as you bring in orientation and scale.
Yeah.
And so either you want to learn this early in life, or you might even want it genetically determined, or some hybrid of the two.
But it could be I learned it early in life, and I've gone through a slow learning process. But once I've learned it, it's going to work for most of the things, right? So it's an upfront learning cost.
Yeah.
But it's quick after that.
Yeah.
All right. So to make that distinction.
Yeah. So like the difference here is here, you learn this elaborate circuit, and then you want the ability to just input different spatial relationships into it, input different displacements into it. And so if it's hard, then it's more like this. If it's easy, it's more
I
like
guess
this.
I was saying it's a little misleading to say it can be learned quickly and easily. I would say does one require an upfront learning cost? After that, you're quick and easy.
Okay. I was putting the emphasis on the circuit here, the transform circuit. Like can the total connectivity from these cells to these cells that produces this transform, can it be learned quickly and easily?
So I missed, the casual reading of which is incorrect. I read it as, can this transform be learned quickly and easily for new objects? But that's not what you're saying. You're saying the circuitry that I'm going to require underlying everything. So one on the right, it takes a long time to learn, one on the left takes less time to learn, very quick. But for a new object, new scenarios, they're both quick, or at least one on the right is quick.
Yeah, and then just to state maybe what's very clear already, but in this one, the spatial relationships are then being represented in weights or connectivity, something in the connections. Where here it's being represented by a cell population, for example, displacement cells. I would say for both of these questions, I'm not taking a strong stance on it. I'm almost trying to say things that everyone in every camp would agree on. Like maybe neurons do more than we give them credit for. Maybe learning rules in the brain actually can be quite complicated, involving,
I think the more interesting, are you done through all the points you want to make?
Yeah.
To me, the more interesting question immediately I started thinking about, like, okay, what's the future of machine intelligence going to look like? At what point do we say, hey, we can stop using neurons and distributed representations or whatever, and can we start doing it in some sort of cheating way? Because it seems to me pretty clear in my mind that the biology is on the right side. I mean, I can't imagine biology on the left side is doing this. But regardless of that, the question is, oh, well, do we have to do it the way the brain does it here? Or it could be, because we're going to have to do this, can we use the way on the left side? So I was trying to think about the points where this thing on the left side would fail. Because generally I've always found that if you don't stick to the biology, you end up failing.
Well, one big one is unions. It's very difficult to represent unions of poses, for example.
Yeah.
Whereas with this distributed representation, even though there are limitations, we can represent unions. We can deal with uncertainty.
How do they deal with this? But they have a probability thing here. Is that the same, or is that?
I don't think they can deal with unions of poses.
They might have said they need unions, but they need ability to handle multiple hypotheses, right? Union is a solution to the multiple hypothesis scenario. Do they not have a way of doing multiple hypotheses on the left side?
Not multiple hypotheses on the pose. These matrices, they're literally representing each value with a number. And so they don't have a notion of a probability distribution of it. It's either this number or that number.
Yeah.
And that decision is made very early on. So if you think about these deep CNN hierarchies, at the bottom you have pixels and edges. At that point, edges and the next level features, you have to make the decision very early on. You don't have context from above to make the decision.
Is it possible capsules have some sort of redundancy where you have two capsules each representing the same object, and then distribution of possible poses? Single pose here, and each one is a hypothesis. We've been talking about single capsule, single object, as a pose and a probability.
Making sure I heard, are you saying that you'll have two capsules that are both devoted up to, the coffee cup or whatever, and just for purposes of guessing, of having multiple guesses?
Yeah, to allow the union.
That might work. I don't know.
This issue of not having I'm sorry, you're done with it.
Yeah.
This issue of not having the ability to learn, like melodies of invariant melodies, or your example was the
Glasses or the state.
the movements of the objects and so on.
Yeah.
That seems to be a really, really fundamental one, and at the core of all generalization. And I was trying to pick a power. Is that just a consequence of getting rid of putting it into the weights, or is that a consequence of having the single cell representation? There's two things going on here. One is they say, hey, they got rid of this, and they put it in the weights of the cells, or the weights of the synapses. But another one is it the single cell representation, or is it the distributed representation? I'm trying to separate those two. But
They could have they could have just as easily had another one of these.
So you could get that feature with the single cell type of representation, maybe. Anyway, I think it's an important question. But if I had to guess today, I would say in the future machine intelligence I would say it's almost 10 to 1 that we're going to be on the right side of this thing. But I'm not certain about that. So I think it's an important question to ask. And
another question: Do you mean to say that capsules can be quickly and easily learned?
I'm saying I'm making kind of the trivial statement that
I thought that's what you said.
Yeah, that's what.
You disagree with that?
Well, I mean, in the literature, capsules are notoriously finicky and hard to train.
That's not what I'm making the statement.
So I just want to be clear about
quick. Quick is different than hard, right?
Well, it says quickly and easily.
Well, he might easily
So I just wanted to say,
change the numbers.
I think you're saying that the circuit is something fundamental about the circuit, not about capsule.
No, yeah, the transform circuit. So like sensor. I wrote the wrong thing. But I'll finish this just to make sure I'm clear. Sensor, and then what, like our no sense. Sorry, I thought this would be faster. component equals the other R. The simple statement I'm making is that you can get this, you can get these set of numbers by like inverting this and multiplying that on the right.
Yeah, it's not even a learning process, just you can just calculate it.
Yeah, so the transform circuit here, they set it up in such a way where the transform circuit is just a set of weights. It's just this right here, which can be learned using linear algebra.
Why, you mentioned the capsules are notoriously difficult to train. Why is that? What problems they run?
I'm not fully sure. I think it's one of the things that's sort of held them back so far that they're working through. I'm not really
So
sure.
on paper it looks good, but then you actually try to learn these things.
I'm not 100% sure why.
Yeah.
I think it's complicated. They go through this voting process, which is, I think, somewhat complex.
All right.
I found it a little useful to, I mean, I knew majors, I knew this stuff before, but just spending time thinking like this, that like, okay, this is what's going on at like the algorithmic level or something. This is one way of describing a neural population. But how are the neural populations accomplishing that? Oh, like this. But I do find it a little useful thinking up in this level a little bit, just making sure I'm keeping this in mind. The notation can be really nice when you're.
It's very helpful to have that in mind.
Everyone except for me.
'Cause it describes sort of fundamentally what's possible and what's not possible.
Yeah.
Yeah, the thing I presented last Monday, and I will present again, I'm going to tell you that how the image on the retina doesn't depend on the size, because the size of the object, I won't try to explain it all right now. The point is, thinking in these terms made me realize, like, oh, all capsules have to do to predict what they're going to sense is just ignore the S, and everything will work out. That was a terrible presentation. The point is,
Well, there's another, so going on a tangent here.
Yeah.
Another nice thing about one of the capsules versions is, so this represents a transformation matrix from, an affine transformation matrix that encodes scale and translation and rotation. But you can imagine other transformation matrices that are much more general. So if you allow yourself to have more than 12 neurons and nonlinear transformation, we can do a lot of fun stuff like folding and stretching in weird ways and stuff like that. And I think in one of their papers, they're representing a much more general transformation.
I think the units for I think it just has 16 variables.
Yeah, and you can do 16 or 30, and then you can represent almost any degrees of freedom, not just these 12 ones.
Yeah, and I meant to mention that here I'm describing like the kind of principles underlying capsules. I'm describing like the motivation. The motivation of capsules was that they would represent something like this, but then they intentionally leave it very flexible, train it via back propagation, and let it learn whatever it wants to learn. So I may not. Anyway, the point is, I'm describing an idealized version of it. It might not even be ideal, but it's kind of the.
Almost certainly it's not going to work that way. Well, we know it's only going to work this way in the brain. 16 floating point numbers, but it's almost certainly not going to work that way in the future for AI. It just seems, that's the fundamental question I keep coming back, can you build systems that work like that? It just seems like it's going to be issues, but anyway. It was helpful for me, even though I didn't understand all of it, but there's some really interesting ideas in there I thought were nicely sort of laid out. I don't think this is a continuous. I see this more like it's more binary decision between these two. Maybe I'm wrong about that.
Yeah, that's all I got.
Yeah, it reminds me of neural networks in general. I remember when neural networks became hot in the 80s. I was like, oh, I was all excited about it, right? Oh, like people are going to get serious. And then they just stopped. They stopped at this section where it's like, that's not right. You got to keep going. You got to, don't stop and be settled on that solution. And it's like capsules are sort of the right idea, but you don't want them to get stuck because they just stop there and they spend the next 5 years trying to make this work, because this is clearly not the way neurons do this. Although conceptually, you're doing the same right type of calculations, but you might just run into this insurmountable problems if you don't, move towards a distributed representation and full representation of displacements, that kind of thing.
Yeah, it's interesting that it may end up being a clue that. So suppose the answer to this is no. Suppose it is to the right, which is probably the case.
We should get a positive name to our side of the column. Be a no column.
I'm trying to be a little bit self-deprecating in a way.
Okay.
These are two carefully chosen.
I bet it could be A or B. That's not better.
Just put a not, both do not.
I like this. I like to humbly present our proposal.
Okay,
We're humble.
okay.
We're the no side. Not to be too full of ourselves. We're the no side.
Well, it's not like dark, I guess that's nature's proposal. So
Yeah.
We don't have to be humble about it. Anyway, you go ahead.
It's an interesting clue. If you live up in this world and just think about it up here, you might reach a totally different conclusion. Just the clue that this actually might require lots and lots of neurons is like a constraint that would guide you in a different direction. It's interesting to me.
Yeah, but what did they do that? Because, take back propagation. How did back propagation come about? It's because they had sort of a network property they wanted, and they said, how can we get that? There was an energy minimization or something like that. And then they said, we'll make it up, and then we'll try to fit the neurons to that. And then people are still trying to fit the neurons to that, right? So instead of saying, hey, that's not the way the brain does it, let's think of that. They just say, no, this is what the math does, and let's fit the neurons to the math. And you'd hope that, it might get stuck there again. They can say, okay, this is what the math says we have to do, and let's make the neurons fit to that. And I don't think they'll sit around and go, hey, but that's not the way real neurons work. They'll probably say, well, we can just, hook them up this way and try to get them to work that way.
I think it's not just about fitting the math, it's also about fitting the current hardware we have. So we don't have this hardware to support this huge distributed representations. So we're just fitting to the hardware we have now so we can run the models now.
I don't know, maybe, but it seems to me, Lucas, that if you go back to the history of, back propagation, no one sat around and saying, hey, we can't do this the right way, so we're doing this temporarily. It's more like they didn't care what the other way was. It was like, hey, it's working, it's doing something, that's it, we're not even interested. So I'm not sure I agree with you. I think, your observation maybe hardware couldn't do it, but I don't think that's what motivated them. I don't think that. I don't know. It doesn't feel that way to me. It feels like, okay, we'll have another mathematical concept that we know has to be solved. So how do we just say the neurons are doing that and distribute it? That's what it feels like.
When these guys talk about capsules, do they ever talk about any way to build these systems such that they're robust to noise or occlusion? This seems like one of the obvious limitations of this kind of super dense representation is that you lose one cell and you've lost the entirety of it. You can't represent the object anymore because you have so much information in one floating point number. Is that something they care about or discuss?
So when you're talking about noise, you're talking about like the cell's values are corrupted.
Yeah, you kill one cell, you've lost representation.
I don't know if they've talked about that. You talk about occlusion. I don't have a direct answer to that, but they do have really good segmentation of, for example, if you overlay digits on top of each other, being able to segment the different digits, being able to see, that's a 7 on top of an 8. That's like kind of their specialty or one thing they can uniquely do. As far as I know, it's unique. I'm not well read. So that's not quite occlusion, but it's related.
Yeah, the first thing you said, what I was really intending was if you lose a cell, you lose the representation, which is not sure on the right side of the board.
Yeah.
Or robust noise.
Yeah. Of course, if you come from a computer science background, right, you're used to that, right? In computers, you get one transistor or gate or something goes dead, and they'll think it's fail. It doesn't bother people.
I think at least for
from a brain point of view, it's not right, but
at least for some people, I think that they know that the neurons aren't representing these digits. They know the neurons are actually doing something a little more like this, but they might think that they might think that it's not maybe each of these neurons is actually represented by like 4 neurons down here rather than thousands being down here. The point is they're like, this is the fundamental algorithm. Somehow biology makes it robust by using multiple neurons. They don't think too deep on this, but the point is they know that if you kill one of these digits, it's gonna all come crashing down.
So this gets,
and they assume that that's all.
what are you guys doing right now? You're working on adding sort of concepts of sparsity, but one could argue also working on concepts of distributed representations and the robustness that comes to them, right? And so maybe you have to, maybe that's a foundational element, right? You have to have distributed representations, or they have to be sparse, and that is a constraint that has to be applied to all future AI systems. And in which case, if you accepted that constraint, then you wouldn't say, oh, I can just get away by having 4 neurons representing it. So you'd have to say, I have to go in this direction. It's you can do the math, but you have to go and deal with these kind of distributed representations. That would lead to different solutions from what we see. I mean, that's maybe, I'm trying out what our position would be on this. We might say, hey, you can do all this great stuff, but it's going to have to be distributed representation, as far as distributed representation.
Another question relating, I think goes to both the capsule side and the HTM side. I'm curious whether they ever talk on the capsule side about representing the same objects at multiple poses at the same time.
That's one of the core things that they admit is. So a capsule can't do that. If you ask someone, any of the papers kind of is apologetic about this. They're like, they're saying that a capsule can't represent like there's a pen and there's another pen next to it or something like that, and that are like right next to each other. In order for it to do that, you would have to have in the same sense that a convolutional neural net split segments space into different squares, the pens would have to be in different squares for it to be able to represent that. So they point to the fact that that in the actual brain, crowding is a thing where, like, if something's off to the side and you have 2 objects that are like close to each other, you can no longer tell that there are 2 objects, that kind of thing. But the point is, no, that is one of the weaknesses of it. That's like kind of an elephant in the room that they're very aware of, and it's like their bet that the system is still going to work despite the fact that it can't represent 2 of the same object that are too close to each other.
Even if they're far apart, you still need to represent the pose of there's a mug here, there's a mug across the street. Same object, different pose. So is the closeness really the critical part, or just the fact that there's more than one?
Couldn't you attend to one versus then the other? Would that work if you attend to one, then attend to the other?
But doesn't your representation have to include the fact that there's 2 mugs?
Well, I think that it could include that if you attend to one and attend to the other, then you'd say, oh, there's these 2 objects that are in some relationship to each other. I'm not sure.
I mean, that is a good point, that if you have like these grandmother mugs at the you have these mug capsules up at the top, and their job is to represent what's in the photo. Yeah, you're right. It feels like a fundamental limitation that those mugs, those capsules at the top don't have any way of saying there are 2 mugs in this photo. I'm guessing they have an answer to this, but that's something that is part of capsules. There's one of their core weaknesses that they've chosen to go with because of the other benefits, and they think that they're going to get the system to work.
It's a general weakness of convolutional systems, and they put in attentional mechanisms and things like that, I think, to get around it.
This sort of hints at, you can imagine, this brainstorming, you can imagine sort of like AI brain manifesto or something like you say, okay, how do we get these 2 worlds to come together? But written from the perspective of a machine learning person, not from a neuroscientist person. And from the perspective of a machine learning person, you could say, just like you did today, say, well, here's the problems, and here's the math, and here's what we have to accomplish. But here's why you have to do certain things the way the brain does it. Here are the constraints that you will not be able to, solve this problem. You can't do these functions using grandmother cell type things because of X, Y, and Z, and therefore you have to do this. Something along those lines where a machine learning person could read this and respond to it. I'm just throwing an idea that just occurred to me, like, how do we bring these worlds together? How do we describe this in a way that machine learning people pay attention to these things.
So I have a chart that has kind of the components of that.
Yeah,
It's the kind of fundamental problems with deep learning and how these brain-related things.
I know you do, it, so I'm thinking
So
about
you could kind of write that out into prose.
but it has to be written out in a more technical form, I think it was. You know, how do you get people to pay attention to it, you know, I don't know.
Those would be good guideline principles. We can like show the community and showing everybody.
Mhm.
I was thinking more of a technical sort of manifesto, if you will, you know, I don't know, like, right now you have these concepts. This is a bit more down in the details here, but I'm not saying, I'm just pointing out that I'm struggling to think, you know, I'm familiar with how machine learning people think, at least somewhat, and why they don't pay attention to the biology or, you know, have it in the past. And, you know, as Mark was just saying, oh yeah, they're aware of this problem, but they're hoping that they can resolve it, type of thing. Well, maybe they can't, then can we show why they can't resolve it? I don't know.
What is the HDM handling of this multiple object representation problem? How do we respond to making it 2 months in a representation?
I mean, one way would be for one thing, this lives in the world of things we brainstorm on, but there's a very straightforward way. That's layer 6A, which is like which could be representing like where is my sensor relative to this water bottle. If there are 2 water bottles, you just activate 2 locations. A union of like, okay, it's right here relative to this one, and it's like right here relative to this one. So a union is one way that you can represent 2 of something, because it's just 2 locations, and it'll successfully predict your sensory input as you move from one to the other.
Wouldn't another way also be through the whole attention and displacement cell type of thing? I mean, we attend to one object, and, you know, I look at a complex scene, I don't see everything. You just don't. And what you can do is then you tend to things, as you tend to things, you're building up this sort of temporary representation of the layer 5 union idea, where you say, these are all the displacements that I've just seen in this frame. This is this relative to this, and this relative to this, and this relative. As you tend to them, and you build up this non-learned but momentary representation of this scene. Then until you learn it, it's not like, you can't recognize it. I had this example, I should show it again, where I flashed an image of a street scene in front of you on the screen. And you get to see it for half a second, it goes away. And you say, oh, that's a street scene, but then none of the details you see, none of them. And then I put up a little, before I put up the scene, I put a little box on the screen. And I say, now I want you to tend to look at the center of the screen at this point and tend to this box. And then I flash it up again. And then you say, oh, there's a word there. I recognize the word. Or there's a dog there. You didn't see those before. So it sort of shows that you have to attend to see these things. I never knew there was a dog in the scene until you attend to the dog, into the area where the dog is. And you didn't even have to know it was a dog. You just had to know that I had to attend to that area, even if I was looking someplace else, and all of a sudden you see there's a dog. So I think there's this idea that you see all these things at once. I'm not disagreeing with Marcus, but I'm saying when you see all these things at once, it's not really true. We only have that effect after we look around really quickly. Now I see all these things out there. And then if you've learned it, then you can say, oh, I recognize this thing, and I know there's 2 cups, because there's always 2 cups. I don't have to see them. I don't have to attend to them, because I recognize the ensemble as a new object. Right? So I can look out of the scene, and I don't have to attend to the marquee of the theater or the top of the courthouse, because I know they're there. And so I know that they're there, because I've learned that structure, not because I just saw them.
It's funny. I could rephrase what both of us just said. We said 2 totally different things. I said, here's one way Capsules could solve this. That if they could represent a union of poses, then it would work. And you said, this is not what you said, but I'm saying you said, you were like, so we just need to add attention to Capsules, and then the problem will be solved for Capsules as well.
Well, I think attention plus the idea of, I don't know if Capsules captures the whole displacement concept very well. I mean, because I'm still confused by this, that they don't have a displacement representation, they only have these in the synapses. I'm still confused by that a little bit. But the idea that you have a momentary displacement representation, and then you have another one and another one, and somehow you can remember those or form a union of them. This is your idea, so.
Yeah, I know.
It sounds like they puzzle me.
I guess got it, okay.
I mean, I just think, when you look at a complex scene, you're not representing all these possibilities at once. I don't think that's true. You have to, I think you have to attend to the different components, and then build up from there. Anyway, all speculation on these things, but.
All right, well,
That
I
was
think we're
good.
done.
I like that, Marcus, that was good. Thanks for doing that.
I feel like I compressed my mental model of things of this, and now I can leave it behind and talk
Don't forget
properly about
Go
it.
back to it.
It was compressed, so now I can keep
It needs
it.
to be in an archived form that's easily retrieved.
Thanks, you guys.
Matt, you want to ride home?
Yeah, go ahead and give me a ride home. I'm gonna log off.
Okay.
All right, that was the research meeting for July 1st, 2019. I'm gonna cut the stream, and I'm gonna come back after lunch, and we're gonna be writing the pros about spatial pooler. So if you wanna learn about spatial pooling, how it works, I'm gonna be writing up the description for the Building HTM Systems tutorial after lunch. I will create an event so you can see it. Whoops, sorry. Those guys all know that I forgot to log out of the meeting. Anyway, stay tuned. If I'm not gonna continue the stream like I do on Twitch. I'm gonna cancel. I'm gonna stop streaming, and I'll be back later. So we'll have distinct videos for each topic. Thanks for watching, everybody.